As a third example, let us find the equation of the line of intersection of the planes pi 1, that is x plus y, plus 2z is 2, and pi 2, that is x minus y, plus 3z is 1. Okay. Now, when two planes intersect, right, we have one line formed, and clearly these planes are not parallel. They do intersect because the normal vectors 1, 1, 2 and 1 minus 1, 3 are not multiples of each other, so they are not parallel in the first place. So they do intersect, there's a line. Now we can try, okay, various formulations here. Let us try the parametric form. Okay, I will not derive one of them and get the others from it, but I will rather get each of them separately from the original formulations. Well, parametric form means that you have a parameter and so on. So let us take, say we take x as the parameter. Then, of course, the first equation becomes t is, okay, that is x, 2 minus y minus 2z. The second equation becomes 1 plus y minus 3z. Okay. Because they are both t, okay, solving both equations at the same time, it says that 2t, okay, is 3 minus 5z. Just adding. So z is, okay, what does that give us? 3 minus 2t divided by, actually, I want t only. Okay, so t is 3 minus 5z over 2. Okay, and what is y at the end? Well, these two are equal. Okay, so we can, okay, solve for y from any of those two things. So from the second one, okay, we have t 1 plus y minus 3. Now instead of z, okay, I can put what I have here. That is 3 minus 2t over 5. So it says that, okay, actually I was looking for the parametric formulation, so I don't need to do these things, it's okay. Right, so x is t, that is fine. From here I can solve for z in terms of t, and from here I can solve for y in terms of t, namely y happens to be t plus 3 minus 2t over 5, okay, minus 1. Okay. So this formulation, x is t, okay, and from here, of course, I didn't need this, but it's okay. I have z easily solvable from here. That's 3 minus 2t over 5. So this is the second one. And finally, this is the third one. So I wrote x, y, and z in terms of t. Well, this is parametric formulation. Okay. Called the symmetric formulation. Okay, it says that I will have actually two equations, okay, but the expressions in them will be all equal to each other. So let me start from the original one. Okay, in the original one, I can eliminate one of them and get these symmetric forms. Again, for example, I can choose, say, x to be t. So t is, this time, x. And again, from pi 1 and pi 2, okay, we get t, or maybe directly, okay, by subtraction. Okay, we get x's go away, so we have 2y minus z is 1. Okay, subtracting pi 2 from pi 1, both of them must be satisfied. So it is 2y, x's cancel, minus z and plus 1. So this says that y and z are related. But on the other hand, okay, t is x, and I have this relation. So again, from pi 1, say, we get x plus y plus 2z equal to 2. Okay, this is my t already. That is my x. And I can replace y in terms of z. So, okay, this says that using these two equations, I can eliminate one of them. What I'm aiming at? I'm aiming at writing t equal to in each case so that I can equate things. Now, from these two things, okay, I can, well, multiply this by 2 and add. So 2 times 2y minus z would be 2. And the other one would be x, that's t, plus y plus 2z is 2. Okay, adding, we get 5y, z's cancel out, I have a t somewhere, and I get 4. Okay. So then, I have the following formulation. T is, okay, I'm of course repeating a few calculations here. T is then, in symmetric form. From the first one, it is x. But t is also equal to, okay, from the last one, 4 minus 5y. And, okay, t is, say, from this one. Well, what is that? We can use, say, pi 2. That would be also fine. Here, from pi 2, I have t minus y plus 3z is 1, or t is 1 plus y minus 3z. I already know the value of y in terms of t, that is 4 minus t over 5. Okay. So from here, I can find t. Okay. As a function of z. And then go back and put it here. So this would be the symmetric form. Now for the vector form. Well, we can use these forms to get the vector form, but as I said, I will not do that. Actually, I will argue here from a vector point of view. So, for the vector form, let us argue directly. Well, the geometry says the following. I have one plane, okay, and I have some other plane intersecting it. Okay. This is, say, pi 1, this is pi 2, and of course, the intersection line would be this one. Well, there is a normal vector to pi 1, and there is a normal vector to pi 2. Now, L lies on both of them. This means that, okay, any vector parallel to L will be perpendicular to N1. Because if this is pi 1, this is L, and this is VL, which is parallel, and this is N1 perpendicular. Of course, N1 would be perpendicular to VL. Similarly, N2 is perpendicular to VL. But we don't know VL, we want to find it, so take VL as N1 cross N2. Okay. A vector perpendicular to two given vectors is most easily found by the cross product. It's a property of the cross product. So then, okay, we can take VL as the determinant of N1. Well, what is N1? Looking at the equation of pi 1, okay, we have it up there. So that would be 1, 1, 2. The other one, the normal to the second one, is 1 minus 1, 3. Okay. And we calculate this cross product. That would be 5, and that would be minus 1, and that would be minus 2. Okay. Now, we also need a point, P0 on L. Well, on L, there are infinitely many points. If we find just one of them, it's sufficient. So how do we find it? Well, this will be a point which satisfies both the equations of pi 1 and pi 2. Well, we have two equations and three unknowns, which means that one of them is free, so we can give it any value we want. Okay, so let us choose the easiest path. Say z is 0. Okay. Since two equations and three unknowns, okay, one coordinate is free. So we can assign anything to it. Well, let me write here a word of caution, because sometimes when you eliminate one variable, okay, the line will not pass, will not intersect that plane. they can be parallel, so there will be no intersection. But that comes from calculation. Let us see if we hit some problem. Let us try. So let me say we try z is 0. Now, pi 1 says that x plus y is 2, and x minus y, that's pi 2, is 1. Okay, so solving, 2x is 3, x is 3 over 2, and if x is 3 over 2, y is 1/2. Okay. So, conclusion, P0 can be taken as 3 over 2, 1/2, and z. Finally, the equation is okay, P is P0. Now, that is 3 halves, 1/2 and 0, plus T, parallel vector, which is 5 minus 1 minus 2. Okay. So this is the vector form found directly. If you do further calculations, you can show that, if all calculations are done correctly, that they're all equivalent to each other. Okay. Well, a fourth example would be, let us find the equation of the plane containing the line L, that is x minus 1 is 1 minus 2y, and that is z over 2, and P0, that is 1, 0, 1. Okay. Now, first of all, is there just one plane containing both of them? How can we have a problem? We can have a problem as follows. If we have our plane, it will contain L, so L is somewhere here on it, and we have a point P0. If P0 is here, no problem. Together, they determine a plane. If P0 is on the line, they do not determine a single plane. They determine infinitely many planes. So you can check easily whether P0 is on the line L. Put 1, you have 0. Put 0, you have 1. It's not satisfied. So P0 is not on the line. So we are rest assured that there is exactly one plane which contains both of them. Okay. Well, the idea is certainly to find a parallel vector, because we already know one point, okay, of the plane, a perpendicular vector to the plane, because we already know one point. So what is a perpendicular vector? Since P0 is given, we need a perpendicular vector to the plane. Let me give a name N to it, to the plane. Okay. Well, how can we find a perpendicular vector? If we can find two vectors on the plane or parallel to the plane, their cross product is perpendicular. So, okay, first of all, there is one vector which is parallel to L given so that it's parallel to the plane. So if we can find another vector parallel to the plane, their cross product will be what we will take as our N. Well, for this, actually, we don't need all of L. If we can find just one point on L, say P1, then the vector P0, P1 will be on the plane, and it will be non-parallel to L. So their cross product will give us N. Okay. So if we find a P1 on L, then P0, P1 and VL, okay, are parallel to the plane. So N can be taken as, okay, P0, P1 cross VL. So the first task is to find a point on L. Well, that's not difficult here. You can easily observe that if x is 1, y is 1/2, z is 0, everything is 0. So it's, of course, a point on L. So taking actually T0, okay, we have 0, x minus 1, that is 1 minus 2y, that is z over 2. So, okay, so P0, which is 1, which is 1/2, which is 0, is on L. Well, what is VL? Well, the equation of L is given here. So to find a VL parallel to L, okay, we look at the equation, but the equation is not in standard form. Okay. So we bring the equation in standard form. And what does that mean? Remember, it means the following: x minus x0 over a, y minus y0 over b, z minus z0 over c, then, okay, v is abc. So, note that the coefficient of x, y, and z must be 1. So, to bring it to standard form, we already have x minus 1 over 1. That's no problem. But in the second case, we have 1 minus 2y. Okay. So we take minus 2 out and divide by it. In other words, we have minus 1 over 2 here. We multiply both by minus 1 over 2. This would be minus 1 over 2 plus y. Okay. And finally, with z, we have no problem. It is z over 2. So VL can be taken as 1 minus half and 2. Okay. So we have our VL, we have our P0. Sorry, something wrong in here. P1 will be on L. Sorry, this is P1 that we found. P0 is the given point. So then, having corrected that mistake, we have to calculate, okay, P0, P1 cross VL. That could be the determinant of P0, P1. Well, let us check that. P0 was 1, 0, 1 here. P1 was this one. P0, P1 is P1 minus P0. So it is 0, 1/2, and minus 1. Okay. This is P0, P1, which is P1 minus P0. And VL is 1 minus half and 2. Okay, we can put ijk's here, and 0, 1/2. Minus 1, apply the diagonal approach, okay? We will get 1/2 here, and for the middle one, we will have minus 1, and for the last one, we will have minus 1/2. Okay. Well, so the plane equation is P0P dot n is 0, or that is x minus P0. Remember, P0 is 1, 0, 1, so x minus 1, y minus 0, z minus 1, 1, 0, 1, that's P0. This is P minus P0. Now, dot n says that we multiply it with these coefficients. And that is. So this is the equation of the plane wanted. Okay. Okay. Well, for the next example, let us have an easy definition. Okay. A line L is said to be normal to a plane if it's perpendicular to it. Well, this means, of course, okay, well, consider a plane, okay, and a vertical line to it. Of course, normal to the plane will be parallel to L. So, that is, VL will be parallel to the normal of the plane. Okay. So this is our definition of a normal line. Well, as a fifth example, okay, find the equation of the normal line, okay, to the plane x plus y plus z is 2, and passing through. Actually, we did such problems, but the name is different. Now we use the normal line. Okay. Well, this is obviously, by this remark, trivial. That is, to find an equation of the normal line, we need a parallel vector, but we have that vector to be taken as a normal to the plane. So, take VL equal to n, which happens to be 1, 1, 1 from the equation. So, okay, the line equation is P0, 1, 1, 2, plus T, 1, 1, 1. Okay. That's a trivial application. Well, the next one is, right, a little bit more serious, but not too difficult. Find the equation of the line L, okay, on the plane and perpendicular to L1, where L1 is 2x minus 1 equal to y sorry, plus 1 over 3, which is z over 2. So the picture then looks like the following. We have a plane, pi. Okay. We have a line L on it that is to be found. It's not given. So let me not sketch it at first. We have a line L1 somewhere. Okay. This L1 can be parallel to pi, so they would not intersect, or okay, it will intersect in a general picture. Let us say that this is our L1. Say it intersects. Okay. Now we want to find a line L which is on the plane. So it is something like this to be found. This is on the plane, and it's perpendicular to L1. So we want to find this line. Well, as usual, we need two things for L. Okay? Well, here we did not make the perpendicularity definition for lines, so let me say a few words about that. Okay. Now, two lines in space, okay, can be parallel, obviously, two parallel lines in space. This includes being the same, okay, including okay, being the same lines. So they are parallel means they can be the same lines, okay, or they intersect, which is certainly possible. I mean, two lines can intersect in space, or neither. Now, when you look at the plane, if you have two straight lines in plane, either they are parallel or certainly they intersect. There is no third choice. But in space, okay, if you have two lines which are not parallel and they don't intersect, so it can happen that they look like something like this. Okay? They don't intersect, they are not parallel. Well, in the last case, these lines are called skew lines. So that's our definition of a skew line. Okay. Well, for this problem to be well defined, that is number 6, okay, I will define perpendicularity of two lines at this question to be intersecting and perpendicular. Okay. Because I mean, if we just look at the parallel vectors and they being perpendicular, we could say two skew lines can be perpendicular to each other, but that is against all intuition. So, okay, L perpendicular L1 means they intersect and perpendicular. Otherwise, this problem would have infinitely many solutions. Okay. So then, what do we know about L? Well, L is on the pi, which means that it is perpendicular to the perpendicular vector, the normal vector of pi. Because, okay, this is my pi, it has a normal vector, this is given. I have an L, and I have a parallel vector, VL. Okay. So clearly, VL is perpendicular to M. That's one thing. Well, there's another thing. L is perpendicular to L1, so VL is perpendicular to VL1 because this is parallel to L1 and this is parallel to L. Okay, thus we can take our VL to be N cross VL1. We know both of them, so that will not be difficult. Let us check that. So this would be IJK, okay? Now, normal vector to pi, well, looking at the equation up there, is 1, 1, minus 1. Now, VL1, on the other hand, is slightly trickier because we have 2x minus 1. It's not in standard form, as we already noted. So, if we divide by, or 2, that is, if we multiply both numerator and denominator by 1/2, coefficient of x will be 1. So it is 1/2, 3 and 2. Okay. This happens to be, if you write your IJKs, and 1, 1 minus 1, okay, that will happen to be 5, and then 2 minus half, that would be 3 halves with a minus sign, and k would be 3 minus half, that would be 5 over 2. Okay. So we have a parallel vector. Now, all we have to find is a point. Okay. Now, to find P0 on L, okay, well, we assume that L and L1 intersect. Well, L is on the plane. L1 is not parallel to the plane. How do we know this? Well, VL1 is 1/2, 3, 2. Okay? And normal vector is 1, 1 minus 1. These vectors are not certainly perpendicular. Okay. So let me emphasize this. Okay. Since n dot VL1 is not 0, very easy to check. Okay. N is not perpendicular to VL1. That is, so L1 does not lie or parallel to pi, lie on or parallel to pi. This means that, okay, you have a plane, okay, you don't have a parallel line, it's not on it, so it is something which intersects exactly at one point. So L1 intersects pi exactly at one point, which by definition of L perpendicular L1, okay, must be on L as well. So the next question is, what is this common point of L1 and pi? Okay. Well, this we can find as we did before, so I will not repeat that. I will simply write down what it was. It happens to be, right, let me write it as an answer. As we did before, it can be found by simultaneous solution of the three equations. Two from the line L1, one from pi, and is 4/3, 4 and 10/3. Okay. So L happens to be P is 4/3, 4, 10/3 plus T times VL, which is 5 minus 3 halves and 5 halves. Okay. Continuing our geometric discussions, we will now find the shortest distances. Okay, when we talk about the distance between 2 points, of course, there's a single distance, and we know how to calculate it in 3 space or in 2 space. Now, shortest distance refers to not distance between 2 points, but distance, the shortest distance, between a point or a line or a plane, again with a plane or line. That's to say, the distances, of course, between them will change up to infinity, most possibly, but which one is the shortest one? Okay, let me explain this as follows. Firstly, distance between a point and a plane. Okay, distance always refers to the shortest distance. Well, what do we have? We have a plane. This is quite geometric. And we have a point. What is the shortest distance? Obviously, if you drop a perpendicular, you will reach the shortest distance, D. Okay. The other distances will be much bigger. So, there is, of course, a way which we already considered in our examples. You can write the equation of the normal line through P0, which will intersect the plane exactly at the point where the shortest distance occurs. And then you will find the intersection of the normal line and the plane, but that's a long process. Okay. Vectorially, we can get it in a much shorter way. Okay. Now, the idea is the following. Okay. Take any point P on the plane. And then consider, okay, these vectors. Which vectors, of course? Well, connect P to P0. Okay? Or P0 to P, it doesn't matter for that matter. Okay. Now, let us consider the vector P0P. Okay. And consider this vector. Okay. Which can be taken as n. What do we see? Okay, we see the following structure. Forgetting the plane, we have the following setup. We have a vector A, and we have a vector B, okay? But this is perpendicular. Okay, what is the length of B? B is in the direction of n, or minus n, anything. Okay? This, of course, is by definition the projection of A on n. So, vectorially, okay, B is the projection of A on B, but on n, actually, on n. So this tells us very simply what we expect. Our A here is P0P. So what's the projection on n? Well, B, the projection is A, okay, let me write P0P now, dot the unit vector of n times the unit vector n. So this is what B is. But we don't want B, we want the length of B. So D, which is the length of B, is just P0P dot n over length n. Okay, in absolute value. So this is our formula. So what do? We find any point on the plane. We know the normal. We calculate P0P dot the unit vector in the direction of n. So this is the shortest distance. Okay. So this is rather the easiest one. Of course, a word of caution. If the point P0 is on the plane, clearly the shortest distance will be 0. Because you can take the point itself, which is on the plane, calculate the distance to P0, which is itself, so the distance will be 0. Okay. As a second argument, let us find the distance between a point P0 and a line L. Okay, the geometry looks like the following. You have a straight line L. If the point P0 is on L, of course, the distance is 0. so suppose it's not. Draw a perpendicular to L. Okay. This is the shortest distance, obviously. Now we know a few things. Because we know L, we have a VL, which is parallel to it. Okay. Well, take any point on L. Okay. Now this any point part is there to make our calculation easier. We can choose any point P there. Okay, now let us call this point Q. Let us say this distance is D1, and so on. So what do we have here? Well, if you look at P0P, or PP0, doesn't matter. Okay, then you consider this vector. Clearly, as before, we have a vector PP0 and we have a vector PQ, which happens to be perpendicular at the endpoint. But this is again precisely the definition of projection. So, okay, PQ is the projection of PP0 on, okay, the line L. That is EL. So, okay, PQ is the projection of PP0 on VL. So, PQ, okay, happens to be PP0 or, yes, PP0 dot VL over length VL. It's a projection. VL divided by length VL. Okay. Now, if you look at the distance, we have D1, the length of PQ here. That is, okay, the absolute value of PP0 dot VL over length VL. Okay. So this is our D1. Now, what is D? Well, when you look at here, okay, D is, by Pythagorean theorem, PP0 length squared minus D1 length, D1 squared, under square root. So D happens to be the square root of P0P in length squared minus D1 squared. Okay, I mean, that's because it's a right triangle. Well, this is then, okay, now what is D1 squared? Let us check that. It is this dot product squared. Okay? So, because it's the dot product, it is the length of PP0, the length of the L over the L, okay, times, it's a dot product, cosine of alpha. Here, alpha is the smaller angle between VL and PP0. Okay. Now, of course, we have square, so we have to square it. The whole thing. Right. Now, this VL over length VL is a unit vector. Its norm is 1, so we don't have it. So this happens to be P0P length taken out square root of 1 minus, now we have this squared, cosine squared. Okay. So it is P0P, okay, sine alpha. Now let us see what, of course, VL is. VL is, okay, our VL here, and this is the angle between VL and PP0. So this is actually our alpha. Okay? It's the angle between VL and this one, the smaller one, of course. VL can direct either way. It doesn't matter at all. Okay. So we have then P0P. Well, we take the sine of the angle. Okay. And we have here the vector VL. And alpha is the angle between them. So I can write this as P0P times length of VL over VL times sine alpha, because this is 1. But alpha is the vector, is the angle between VL and PP0. So this is the cross product. That's the length of the P0P cross VL, okay? Where VL is the unit vector here. So let me not say VL, let me say UL. UL is VL over length VL. It's a unit vector. Okay. Then this happens to be the cross product, and that's a nice formula. Okay. Well, we need a point, okay, on the line, any point, it doesn't matter. Just put it and take the unit vector, UL, is not VL, directly, and then take the cross product. The length gives you the shortest distance. Okay. Well, as a last calculation, let us calculate the shortest distance between, okay, two skew lines. Okay. Now let B1, L1, and L2 be two skew lines. So what does it look like? One of them is L1, the other one is L2, but of course this is in space. They do not intersect. Okay? These are skew lines, so they do not intersect in the first place, even though it looks like intersecting, but they're in space. What is the shortest distance between them? It is a distance of the foam which is perpendicular to both. Okay. Of course, this picture doesn't make sense in plane. Okay. Picture is in space. And L1, L2 do not intersect. So we have to be careful there. Well, as usual, this is what we do. We have a P0, so, okay. Right. Suppose this point is Q0, this point is P0. So assume that the shortest distance occurs at the point P0 on L1 and Q0 on L2. So this is my D in question. I take an arbitrary point somewhere here, any point on L2. Call this Q, and take any point here, call it P, again any point on L1. Okay. Now I want to argue in terms of projections again. So forget the whole picture for a minute. Okay? Let us look at the following. P0, Q0, and Q. Okay. Let us look at these two vectors. Okay. Well, what we know, of course, is that this was the line L2, and this was perpendicular. Because, that was the definition of Q0. This tells us that if I take Q0P, P0Q, and if I project it on L2, okay, wait a minute. No. If I take it and project it on this vector, okay, then P0, Q0 would be its projection. So let me write that down. Okay. P0, Q0 is the projection of the vector P0Q along this vector on the vector P0, Q0. Okay. But do we know a vector parallel to P0, Q0? We don't know Q0 or P0. But we don't need them. We only need a vector parallel to it. Well, of course we do. If we look at the picture, okay, a vector in this direction, in the D direction here, P0, Q0, is perpendicular to L1 and it's perpendicular to L2. So, okay, P0, Q0 vector is perpendicular to VL1 and it is perpendicular to VL2. Okay. This means that, okay, it's parallel to the cross product. Do I need the length of P0, Q0? Well, later, okay. But for the time being, I have P0, Q0, just a vector on which I have a projection. So I only need a unit vector in the direction of P0, Q0, which happens to be this cross product, divided by its norm. Okay. So, okay, we can write that P0Q is actually P0, Q0, okay, is actually the projection of P0Q, so it is the dot product with any vector in this direction, call it A, parallel to P0Q. Okay. So this projection is precisely this, where I replaced the vector showing the direction of the projection, P0Q, by any vector parallel to it. Well, we already know a parallel vector. So we take the unit vector, take A to be VL1 cross VL2, and say U is VL1 cross VL2 divided by length of VL1 cross VL2. So I take the normal vector, unit vector, okay, in the direction of P0, Q0, which I know. Okay. So we have P0, Q0, I'm rewriting it. It is P0Q dot U times U. Now, taking norms, the norm of P0, Q0 is D. And that is, when I take the norm, this is a unit vector, remember? It's a unit vector. So when I take the norm, it's just the absolute value of P0 Q dot U. Okay, what do I have here? I found D, but U I know. U is given by this, and I know everything here. I know VL1, I know VL2. Okay, Q is an arbitrary point, okay, taken on L2, it's fine. But this is in terms of P0. And P0 is not arbitrary, and we don't know it. So let us replace P0 with any P. Can we do that? Let us see. Okay. Let us, okay, to P0Q, let us subtract and add some vector. So write P0Q as P0Q, okay, minus PQ plus PQ. I added and subtracted the same vector, so I did nothing. But I know something. This is, okay, P0Q minus PQ. That means, wait a minute, do I want that? I want QP probably. No, that is, okay. Right. This is Q minus P0, and this is minus PQ, so it is P minus Q. Okay. Added. Remember, PQ is Q minus P, but negative of it is P minus Q, which means that this is, okay, P minus P0. That's all. So this tells me that if I continue my equation, it is P0Q, okay, which is adding and subtracting gives me P minus P0 plus PQ dot U. Now, P minus P0, if we look at the picture, is parallel to L1. Because both points are on L1. Okay, this tells me that if I take the dot product with U, remember U is the cross product of VL1 and VL2, so this is perpendicular to VL1. So this is parallel to L1, and this is perpendicular to VL1. VL1 was parallel to L1, okay, so the dot product is 0. So this means that it is PQ dot U. So that's a nice formulation. Remember what we have here. U is the unit vector of the cross product direction. We all know these things. P and Q are arbitrary points, taken one on L1, the other one in L2, so we can easily find the calculation. Okay. Well, there are different ways of representing the distance in terms of a determinant as well. I will not go into that. You can read it in your textbook. By the way, I would strongly recommend that you do not memorize these formulas. Okay, there is no need for it. But understand how they are derived. It's a good exercise to understand them. It shows us the power of the projection.